Hello all, and welcome to another one of my videos where I discuss the difficult concepts that we're going over in class in the SI sessions. I'm looking at a problem on assignment 9, I believe it is, problem 6, where you have to determine the change in energy, total energy, of a circuit as pictured, where we insert a dielectric into one of these capacitors, which both capacitors have an equal capacitance, and then we insert a dielectric into one of them. It doesn't matter which. We also have an EMF source, a battery, which we'll call V, and we want to know what happens to the total energy when we insert that dielectric into that capacitor. And before I get too detailed into that problem, I want to just take a couple steps back and look at some other problems that we may have done. So let's say that you have a battery and you have a capacitor, and you assemble this circuit, okay? Then you're going to charge this capacitor with the battery, and when all is said and done, you're going to have a charge stored on the plates of the capacitor, and you're also going to have an electric field going from the top to the bottom, and you're also, by virtue of that, you're going to end up with a voltage potential across the capacitor. And it's actually the same voltage potential that's across this battery, okay? It's going to impose its potential across that capacitor. We know that the energy stored in the capacitor is going to be a product of the charge and the potential across it. The charge, I should say the charge on it, on one of the plates, multiplied by the potential across it, which is the integral of the electric field from one plate to another, and which is, of course, uniform from one side to the other side. That's because when you have a sheet of charge, the electric field is uniform without regard to distance, unlike a point charge. Okay? So we know that, and let's say we disconnect this capacitor, no green, okay, and we just have the capacitor by itself, not connected to anything. I would argue that, in theory, the charge will be maintained on that capacitor. This isn't always true, and humidity may have an effect on this. If you accidentally make an electrical contact with ground or anything else with a lower potential, then you will discharge this capacitor. And it could be dangerous too. But the fact is that if it's not electrically connected to anything, in theory, it will maintain that charge. Okay? So what's going to happen here is, let's say we pull these plates apart, as we've done before in several examples. You know, just move those, stretch it out. Or let's say we add a dielectric in. What's going to happen? So your capacitance is going to be your electric permittivity times the area of the plates divided by the distance between them, and then maybe also multiplied by a dielectric constant, if it exists. In this case, it's K, so blue, right? Okay. So now you have to determine what happens to the capacitance. Well, if your dielectric is a real dielectric, it's going to have some multiplier, K, associated with it, which is going to give you a higher capacitance. Increasing your distance, D, so if D goes up, then C is going to go down, right? So you have less capacitance if that happens. So that's how it affects it. Now, if you're disconnected from a battery and this happens, your charge, as I said, is going to remain on there. It doesn't have anywhere to go. There's no conduction here. It's just a dead end. So your charge doesn't move. So what does move? Well, your capacitance can also be written as the charge stored on the plates divided by the potential between the plates. I just said your charge isn't moving. So if your dielectric affects your capacitance, or your distance affects your capacitance, the charge is held fixed. That means it can only affect the potential, V. Okay? And that's going to change your capacitance. We know this. We've been over this before. So why is this problem different? Okay, so this is the meat and potatoes of this video. So the battery has a potential associated with it. The capacitors are not disconnected from that source. They are in a circuit. They are conducting electricity. So the charge can be dynamic. The potential cannot be, because it's already been established by the battery. So this is the opposite. When you change the capacitance in this circuit, you're changing the charge on the capacitors as well, where the voltage is fixed. Okay, your potential V, your EMF is fixed. So how do we address this? Well, these capacitors are in series. So let's take a look at what the equivalent capacitance would be for a series circuit. Okay, I'm going to put an S for series. This would be, look something like this, where you would invert the capacitance of each of the two. You'd add that together, and then you would reinvert that. And if you have two capacitors, you can write that as C1 times C2 over C1 plus C2. This does not work if you have more than two capacitors. So you can only use the first one, and that's the more accurate case if you have three or more capacitors in a circuit, in a series circuit, I should say. Doesn't matter if you have parallel branches. That doesn't affect that. I'm just talking about in a series branch. So this is a pretty simplified circuit. Okay? So what about this particular circuit? These capacitors are both valued at C. They are identical. So again, before we put in the dielectric, what does that look like? We're going to call that C EQ, and I'm going to put a 0 because this is going to be proportional to the stored energy in this circuit before the capacitor, or I'm sorry, before the dielectric is inserted. So this is going to be C times C over C plus C. Sorry, that's not right. C squared over 2C. All right, so that is the capacitance before the dielectric. So what about afterwards? So the new energy, U, is proportional with equivalent capacitance. And we're going to attach a K to just one of the capacitors. It doesn't matter which. All right. That is our new capacitance. Okay, so what now? Excuse me, that was my desk. We need to divide U by U naught, which is going to be proportional to, or really equal to, since they're proportional, C equivalent over C equivalent naught. Okay. Can we reduce this at all? I'd say we can. Kc over C, K plus 1, and then you can still, actually, no, I'm sorry. We didn't reduce that properly. We're dividing by C here, so that would be Kc over K plus 1. Okay. That is our C equivalent of the new circuit with the dielectric, and we're going to divide that by C squared over 2C, which is just C over 2. Okay, let's see what that is. So that's what it's going to look like. And we can just multiply it by 2 over C, employ a reciprocal rule, just simple, fractions really. And then our C's are going to cancel. And this is going to be our ratio. Okay, so notice that I addressed this by adjusting the equivalent capacitance in series. Okay? That's what I'm concerned with here. Now, why do that? Why didn't I attack the capacitors individually? Well, the reason for that is because, as I said, the battery establishes the potential in the circuit. The potential of the battery does not change, even though the equivalent capacitance of the two series capacitors does change. However, if one capacitor changes, then it's a different ratio of capacitance between the two. In this instance, they were both C. Then when we insert the dielectric, we have Kc on top, right? This is Kc now. And then the bottom one is just C still. We don't know what K is, so we have to treat it symbolically, right? When we put in K, let's just say, let's try to make it concrete. Let's say K is double, or K is 2, I'm sorry. So it doubles the capacitance in effect. Well, that means that that C1, this top one, has twice the capacitance that the bottom one has. So it's going to have twice the potential across it. But this is not going to, it should not affect the overall voltage. It's going to affect the charge. But if you look at it, separately, then you might get, really confused. So you have to take a look at the overall capacitance and what changes between those, while keeping your voltage the same, which means your charge has to increase. And if you look at the equation for energy, U equals 1/2 CV squared. In this case, our V is constant, and our C changes with respect to what the dielectric does to it in terms of K. And that's our answer. 2K over K plus 1. Thanks for watching.